Imagine holding a piece of gold in your hand. Feel its weight. Observe its lustrous gleam. Now consider this extraordinary thought. What you hold contains secrets that remained hidden from humanity for over 2,000 years. Within that seemingly solid metal lies a universe of invisible architecture so intricate, so beautiful, that when we finally glimpsed it, we discovered we had been living inside the greatest mystery of all. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed because tomorrow I've saved something extraordinary for you. 2,500 years ago, in the olive groves and marble courtyards of ancient Greece, a philosopher named Democritus posed a question that would echo through millennia. He wondered what would happen if you took that piece of gold and cut it in half, then cut one half in half again, and again, and again. Could you continue this division forever, creating ever smaller fragments that retain the essence of gold? Or would you eventually reach something fundamental, something that could not be divided further? This was no idle speculation. Democritus believed deeply that there must be a limit, a smallest possible piece of matter that formed the building blocks of everything we see. He called these imagined particles atomos, a Greek word meaning uncuttable, indivisible. The atom was born not in a laboratory, but in the mind of a man who dared to imagine what lay beyond the reach of human senses. For over 2,000 years this remained pure philosophy. The atom existed only in thought, a beautiful idea with no way to prove its reality. Generations of thinkers debated its existence, while never knowing they were surrounded by precisely what Democritus had envisioned. Countless trillions of these fundamental particles, dancing and vibrating in every breath they took, every surface they touched. The breakthrough came from an unexpected source. In 1803, an English schoolteacher named John Dalton was conducting simple experiments in his modest laboratory. Dalton possessed something that even the brilliant Greeks had lacked: the ability to weigh substances with extraordinary precision. What he discovered would transform philosophy into science. When Dalton combined hydrogen with oxygen to create water, something remarkable happened. The reaction was not random or variable. 8 grams of oxygen, always without exception, combined with exactly 1 gram of hydrogen. Never 8.1 grams, never 7.9 grams. Always 8 to 1, with mathematical precision that seemed to echo the hidden order of the universe itself. This was extraordinary. If matter were infinitely divisible, as many believed, chemical reactions should show endless variation. But here was evidence of something deeper, a granular structure to reality itself. Dalton realized that elements must exist as discrete packages, each with its own characteristic weight. The ancient dream of atoms was becoming measurable fact. Consider the implications of what Dalton had uncovered. Every substance around you, the air you breathe, the water you drink, the ground beneath your feet, all of it constructed from invisible building blocks that combine in precise mathematical ratios. It was as if nature operated according to a secret recipe book, written in a language humanity was only beginning to learn. But Dalton's atoms were still theoretical. No one had seen one, touched one, or directly proven their existence. They remained inference, brilliant deduction from the patterns hidden within chemical reactions. The atomic realm beckoned like an unexplored continent, but explorers still lacked the tools to visit it. The tools began arriving in the laboratories of the 19th century. Scientists developed techniques to study matter in ways the Greeks could never have imagined. They could create vacuums, generate flaknik, powerful electric fields, and measure the properties of substances with unprecedented accuracy. With each new instrument, with each refined technique, the invisible world grew a little less invisible. By 1869, Russian chemist Dmitry Mendeleev had made a discovery that revealed the atomic realm possessed an architecture as elegant as any cathedral. Working with the known elements, made ESD, 63 of them at the time, Mendeleev noticed that when arranged by atomic weight, they fell into repeating patterns of properties. Elements with similar characteristics appeared at regular intervals, like a melody that repeats with variations throughout a vast symphony. But here was the truly remarkable part. Mendeleev's pattern revealed gaps, empty spaces where elements should exist but hadn't yet been discovered. With breathtaking confidence, he predicted the properties of these missing elements, their weights, their colors, how they would behave in chemical reactions. He was, essentially, predicting the existence of atoms that no human had ever encountered. One by one, these predicted elements were found. Gallium in 1875, scandium in 1879, germanium in 1886. Each discovery matched Mendeleev's predictions with stunning accuracy, as if he had somehow read the blueprint of creation itself. Think about what this meant. The periodic table wasn't just a catalogue of known substances, it was a map of atomic reality, revealing that the building blocks of matter followed fundamental laws as predictable as the orbits of planets. The universe, at its most basic level, operated according to principles humanity could understand and even predict. Yet even as the evidence mounted, atoms remained frustratingly beyond direct observation. They were too small, too fast, too alien to our everyday experience. Scientists could infer their existence, predict their behavior, and even weigh them with increasing precision. But the atoms themselves remained invisible, like stars too distant for any telescope to resolve. The challenge was one of scale. If you could enlarge an atom to the size of a football stadium, the particles within it would still be smaller than marbles. We were trying to study a realm that existed at dimensions our minds could barely comprehend, using tools designed for a world of objects we could see and touch. But nature, as we would soon discover, had been offering clues all along. Every time a substance glowed in a flame, every time lightning split the sky, every time the sun painted the horizon in brilliant colors, all of these phenomena were atomic signatures, messages from the invisible realm that surrounded us. We simply hadn't learned to read the language yet. The late 19th century brought new phenomena that would crack open the atomic vault. Strange rays that emerged from evacuated glass tubes, mysterious substances that glowed in the dark and fogged photographic plates, through solid barriers, energy that seemed to emerge from nowhere, defying the established laws of physics. Scientists realized they were witnessing something unprecedented, direct evidence of activity within atoms themselves. These weren't just the simple, indivisible particles that Democritus had imagined. They were complex systems with internal structure, capable of emitting energy and radiation. The atom was not a marble, but a universe in miniature. As the 20th century dawned, the stage was set for discoveries that would revolutionize our understanding of reality itself. New tools were emerging, devices capable of detecting individual particles, measuring their properties, and mapping their behavior. Young minds were tackling problems their predecessors couldn't even formulate. Among them was a brilliant Danish physicist who would soon peer deeper into atomic structure than anyone before him. His name was Niels Bohr, and his discoveries would reveal that the invisible world operated according to rules so strange, so beautiful, that they challenged every assumption about the nature of existence itself. The atomic realm that had beckoned to humanity for over 2 millennia was finally ready to reveal its deepest secrets. And when it did, we would discover that reality was far more extraordinary than even the boldest philosophers had dared to imagine. The journey into the heart of matter was about to begin, carrying with it the promise of understanding forces that shaped not just our world, but the entire cosmos. In learning to read the atomic signatures that surrounded us, we would unlock technologies beyond the wildest dreams of previous generations and uncover truths about existence that would forever change how we see ourselves and our place in the universe. What lay ahead was nothing less than a complete reimagining of reality, one atom at a time. The turn of the 20th century brought with it an extraordinary revelation. The atom was not the end of the story, but merely the beginning. In laboratories across Europe, scientists were discovering that these fundamental building blocks of matter were themselves constructed from even smaller components. It was as if explorers, having finally reached what they thought was the edge of the world, discovered instead that they stood at the shore of an even vaster ocean. In 1897, Joseph John Thomson sat in his Cambridge laboratory, surrounded by glass tubes and electrical apparatus that hummed and crackled with mysterious energy. He was studying cathode rays, ethereal streams of something that emerged when electricity passed through nearly empty glass tubes. These rays possessed an almost ghostly quality, invisible to the naked eye, yet capable of casting shadows and making certain materials glow with an eerie light. Thomson had constructed an elegant experiment. He placed electric and magnetic fields around the path of these cathode rays, watching how they bent and curved in response to the forces. What he discovered would shatter humanity's understanding of atomic structure forever. The rays bent toward positive electrical charges, revealing that they themselves carried negative charge. But here was the extraordinary part. When Thomson calculated their mass, he found they weighed nearly 2,000 times less than the lightest known atom, hydrogen. These mysterious rays weren't atoms at all. They were fragments of atoms, pieces so small that their existence had never been suspected. Thomson had discovered the electron. For the first time in human history, someone had found direct evidence that atoms contained smaller particles. The indivisible building blocks of Democritus were divisible after all. Atoms had internal architecture. Consider what this meant for our understanding of reality. Everything around you, your body, the chair you sit in, the air you breathe, all of it constructed from atoms that were themselves constructed, from even tinier components. It was like discovering that every grain of sand on every beach was actually a miniature city, complete with its own intricate structures and moving parts. Thomson proposed a model for this newfound atomic complexity. He envisioned atoms as spheres of positive charge with electrons embedded within them, like raisins distributed throughout a pudding. It was an elegant solution to the puzzle of atomic structure, and for a time it seemed to explain the experimental evidence perfectly. But nature, as we so often discover, is far more inventive than our first attempts to understand it. 14 years later, in 1911, Ernest Rutherford conducted an experiment that would revolutionize atomic theory once again. Rutherford had discovered that certain radioactive elements naturally emit alpha particles, essentially the nuclei of helium atoms, carrying positive charge and considerable mass. He decided to use these alpha particles as microscopic projectiles to probe the interior structure of atoms. Working with his assistants, Hans Geiger and Ernest Marsden, Rutherford fired streams of alpha particles at an extraordinarily thin sheet of gold foil, so thin it was only a few hundred atoms thick. According to Thomson's model, these particles should pass through the gold atoms like bullets through a cloud, perhaps deflecting slightly as they encountered the diffuse positive charge within each atom. What they observed defied all expectations. Most alpha particles passed straight through the gold foil, just as predicted, but a tiny fraction, approximately 1 in every 8,000, bounced backward, as if they had struck something incredibly dense and immovable. Rutherford later described his astonishment. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The implications were staggering. The atom was not a uniform sphere of positive charge with electrons sprinkled throughout. Instead, all of the positive charge and nearly all of the atom's mass were concentrated in an incredibly tiny region at its center. the atomic nucleus. The rest of the atom was essentially empty space, with electrons somehow occupying the vast emptiness around this dense core. To appreciate the scale of this discovery, imagine scaling an atom up to the size of a football stadium. The nucleus would be a marble sitting at the center of the field, while the electrons would be tiny specks circling somewhere in the upper reaches of the stadium. Everything else, the entire volume of the stadium between the marble and the distant electrons, would be completely empty. This revelation transformed our understanding of matter itself. The solid objects around you, the very ground beneath your feet, are almost entirely empty space. The sensation of solidity that you experience comes not from atoms packed tightly together like bricks in a wall, but from electromagnetic forces acting across the emptiness between atomic nuclei and their distant electrons. Yet Rutherford's discovery created a profound puzzle that seemed impossible to solve. According to the established laws of physics, electrons carrying negative charge should be irresistibly attracted to the positively charged nucleus. They should spiral inward in a death dance lasting less than a billionth of a second, causing every atom in the universe to collapse catastrophically. But atoms were stable. They had existed for billions of years without collapsing. Stars continued to shine, planets maintained their orbits, and life flourished across the cosmos. Something was preventing the universal atomic collapse that classical physics predicted with mathematical certainty. The problem haunted the greatest minds of the era. How could electrons maintain their distance from the nucleus? What force or principle kept them from spiraling inward to their doom? The answer would require thinking that challenged the very foundations of physics itself. Meanwhile, other discoveries were providing clues about the hidden behavior of atoms. When elements were heated until they glowed, they didn't emit all colors of light equally. Instead, each element produced its own unique signature, specific wavelengths of light as distinctive as fingerprints. Hydrogen glowed with precise colors, a deep red at 663 nanometers, a blue-green at 486 nanometers, and a violet at 434 nanometers. These spectral lines, as they became known, revealed that atoms were not chaotic systems but entities governed by hidden order. The light they emitted followed mathematical patterns that suggested underlying structure and organization, yet no one could explain why atoms chose to emit only certain colors while ignoring others. The mystery deepened with the discovery of quantum effects. Max Planck had shown that energy came in discrete packets, quanta, rather than the smooth, continuous flow that classical physics expected. Albert Einstein extended this insight, demonstrating that light itself consisted of particles called photons, each carrying a specific amount of energy. These quantum phenomena hinted at a fundamental graininess to reality, as if the universe operated more like a digital system than the analog mechanism that scientists had long imagined. Energy, matter, and even space and time might have smallest possible units, just as Democritus had proposed for matter itself. By 1910, the stage was set for a revolutionary breakthrough. The experimental evidence was clear. Atoms contained electrons orbiting dense nuclei, yet remained mysteriously stable despite the electromagnetic forces that should have destroyed them instantly. The spectral signatures of elements revealed hidden patterns that classical physics couldn't explain, and quantum effects suggested that reality itself operated according to rules that defied common sense. What was needed was a mind bold enough to abandon classical thinking and embrace possibilities that seemed to violate everything we thought we knew about the physical world. That mind belonged to a young Danish physicist whose revolutionary insights would transform our understanding of atomic structure and lay the foundation for technologies that would reshape human civilization. The invisible world was about to reveal its deepest secrets, and with them, principles so strange and beautiful that they would challenge our most basic assumptions about the nature of existence itself. The age of quantum mechanics was dawning, and at its heart lay discoveries that would prove even more extraordinary than the boldest explorers of the atomic realm had dared to imagine. The greatest adventure in the history of science was about to begin, led by a brilliant young man who possessed the rare combination of mathematical genius and imaginative courage needed to peer beyond the boundaries of the known world and glimpse the quantum reality that lay hidden within every atom in the universe. On October 7th, 1885, in the elegant streets of Copenhagen, a child was born who would one day peer deeper into the heart of matter than any human before him. Niels Henrik David Bohr entered a world where curiosity was treasured like the finest porcelain, where intellectual discourse flowed as freely as wine at the family dinner table. His father, Christian Bohr, was a professor of physiology at the University of Copenhagen, a man fascinated by the mechanisms that powered life itself. His mother, Ellen Adler Bohr, came from a prominent Jewish banking family, bringing to their home the cosmopolitan culture of educated European society. In this nurturing environment, young Niels developed an insatiable appetite for understanding how things worked, from the intricate clockwork of timepieces to the vast mechanics of the cosmos. But Niels possessed something beyond mere intelligence. He had the rare gift of being able to hold contradictory ideas in his mind simultaneously, to embrace paradox as a pathway to deeper truth. This quality would prove essential when he encountered the bewildering world of atomic physics, where common sense became an unreliable guide, and reality operated according to rules that seemed to defy logic itself. As a young man, Bohr excelled at everything he attempted. He was an accomplished footballer, playing goalkeeper for the Akademisk Bold Club, where his analytical mind proved as valuable as his athletic ability. He would study the patterns of opposing players with the same methodical attention that he later brought to atomic structure. Even in sport, he was learning to see the hidden order beneath apparent chaos. After earning his doctorate in Copenhagen in 1911, Bohr embarked on what would become a pilgrimage to the great centres of physics. He travelled first to Cambridge, hoping to work with J.J. Thomson, the discoverer of the electron. But Thomson, already an established figure, showed little interest in the earnest young Dane's ideas about atomic theory. Undeterred, Bohr made his way to Manchester, where Ernest Rutherford had established a laboratory that hummed with radioactive energy and revolutionary thinking. Here, surrounded by the apparatus that had revealed the atomic nucleus, Bohr found the intellectual home he had been seeking. Rutherford, despite his gruff exterior, recognized brilliance when he encountered it, and he welcomed Bohr into his circle of young researchers who were remaking physics from the ground up. In Manchester, Bohr confronted the great puzzle that had been haunting atomic theory since Rutherford's gold foil experiment. How could electrons orbit the nucleus without spiraling inward to their destruction? Classical electromagnetic theory predicted that accelerating charged particles, APB, and orbiting electrons were certainly electrons. Accelerating, UB, should continuously radiate energy, gradually losing speed until they crashed into the nucleus in a catastrophic finale, lasting mere fractions of a second. Yet atoms persisted. They had survived for billions of years, maintaining their structure through cosmic epochs while stars were born and died around them. There had to be something fundamentally wrong with the classical picture, some hidden principle that stabilized the atomic world. Bohr made a leap of imagination that would transform physics forever. What if, he wondered, the classical laws simply didn't apply at atomic scales? What if electrons could only occupy certain specific orbits around the nucleus, like runners confined to predetermined tracks? Between these allowed orbits would lie forbidden zones where electrons simply could not exist, no matter what forces acted upon them. This was a revolutionary proposal. It suggested that energy itself came in discrete packages at the atomic level, that there were smallest possible amounts of energy that could be absorbed or emitted by atomic systems. Bohr was proposing that the quantum nature of energy that Planck had discovered in his studies of radiation was fundamental to atomic structure itself. Consider the audacity of this idea. Bohr was suggesting that an electron orbiting an atomic nucleus behaved more like a planet following a predetermined celestial track than like a classical particle subject to continuous forces. The electron could exist in the first allowed orbit, or the second, or the third, but never in the spaces between them. It was as if nature operated according to a cosmic zoning law that prohibited certain configurations while mandating others. But Bohr's model did more than solve the stability problem. It explained one of the most beautiful and mysterious phenomena in all of physics: the spectral lines that elements produced when heated to incandescence. When an electron absorbed exactly the right amount of energy, it could jump from a lower orbit to a higher one, not gradually, but instantly, in what came to be called a quantum leap. The electron simply vanished from one orbit and appeared in another, with no time elapsed and no path traced between them. When the electron later fell back to a lower energy orbit, it released that absorbed energy as a photon of light, with a frequency precisely determined by the energy difference between the two orbits. This explained why hydrogen glowed with such specific colors when heated. The deep red light at 663 nanometers came from electrons jumping from the third orbit to the second. The blue-green light at 486 nanometers resulted from jumps from the fourth orbit to the second. The violet light at 434 nanometers emerged from fifth to second transitions. Each color corresponded to a specific quantum leap between allowed energy levels. Bohr's equations didn't just explain these wavelengths. ES predicted them with extraordinary precision. For the first time, someone had created a mathematical model that could calculate exactly which colors an atom would emit, based purely on theoretical understanding of its internal structure. It was as if Bohr had discovered the hidden musical score that atoms followed when they sang their songs of light. The implications were staggering. Every rainbow that had ever painted the sky, every aurora that had danced across polar nights, every flame that had flickered in human hearths throughout history, all of these displays of color emerged from quantum leaps occurring trillions of times per second in countless atoms. The beauty of light itself was a manifestation of the quantum architecture that Bohr had revealed. But perhaps the most profound aspect of Bohr's discovery was what it revealed about the nature of reality itself. The quantum leaps that his model described violated every principle of classical physics. Electrons didn't gradually accelerate from one orbit to another, they simply appeared in their new positions instantaneously. There was no classical explanation for how this could happen, no mechanism that could account for such discontinuous behavior. Bohr was uncovering evidence that the universe operated according to fundamentally different rules at its smallest scales. The smooth, predictable world of classical physics was merely an approximation that worked well for large objects but broke down completely when applied to atomic systems. At the quantum level, reality was granular, discontinuous, and filled with sudden transitions that defied conventional understanding. This realization would lead Bohr to develop one of the most profound insights in the history of science: the principle of complementarity. He recognized that atomic particles couldn't be understood using any single classical concept. Sometimes electrons behaved like particles with definite positions and trajectories. Sometimes they behaved like waves spreading through space and time. The complete description of an atomic system required embracing both pictures simultaneously, even though they seemed mutually contradictory. Bohr's atomic model marked the birth of quantum mechanics, a new branch of physics that would revolutionize our understanding of reality and enable technologies that previous generations could never have imagined. From the transistors that power modern computers to the lasers that carry information through fiber optic cables, from medical imaging devices that peer inside the human body to solar panels that convert sunlight into electricity, all of these innovations trace their origins to the quantum principles that Bohr first revealed in his study of Prempries, atomic structure. But in 1913, as Bohr published his groundbreaking theory, none of these applications were even distant dreams. He was driven purely by the desire to understand, to glimpse the hidden architecture of matter and uncover the mathematical principles that govern the behavior of atoms. He had no way of knowing that his discoveries would ultimately transform human civilization itself. The young physicist from Copenhagen had opened a door to a realm where the impossible became routine and where the very foundations of reality operated according to rules that challenged human intuition. As news of his discoveries spread through the scientific community, it became clear that the age of classical physics was drawing to a close, and the quantum era was about to begin. The atom had revealed its first secrets, but they were secrets unlike anything anyone had expected. The journey into the quantum realm was just beginning, and it would lead to revelations that would make even Bohr's revolutionary insights seem like the opening notes of a symphony whose full magnificence was yet to unfold. The morning of April 9th, 1940, dawned clear and cold over Copenhagen. In the early hours, as the city still slumbered beneath a blanket of Nordic calm, few could have imagined that this day would mark the beginning of the darkest chapter in Denmark's modern history. But across the Baltic Sea, a massive military operation was already in motion, one that would transform Niels Bohr's life from that of a peaceful scientist into something resembling a character from an espionage thriller. At 4:15 in the morning, German warships appeared like grey phantoms in Copenhagen harbour. Operation Weserübung had begun, Hitler's lightning assault on Denmark and Norway. Within 6 hours, Nazi forces had accomplished what many thought impossible: the complete occupation of an entire nation with minimal resistance. Denmark became the fastest conquest in Nazi military history, falling before most of its citizens had even awakened to the danger. For Bohr, now 54 years old and director of the Institute for Theoretical Physics at the University of Copenhagen, the occupation represented a catastrophic transformation of his world. His institute had become far more than a centre for atomic research. Inventor. It was an intellectual sanctuary where the greatest minds of the 20th century gathered to explore the frontiers of quantum mechanics. Einstein had walked these halls. Heisenberg had debated the uncertainty principle in these very rooms. Scientists from across Europe had found refuge here when political storms threatened their work elsewhere. But the Nazi occupation changed everything. Bohr's mother, Ellen, had been born into the prominent Adler banking family, a Jewish family whose prominence now made them targets of the Nazi racial laws. Though Bohr had never practiced Judaism and considered himself thoroughly Danish, his Jewish heritage marked him for persecution under the twisted ideology of the Third Reich. More immediately dangerous was the nature of his scientific work. Bohr's insights into atomic structure had laid the foundation for understanding nuclear physics, and nuclear physics held the key to weapons of unimaginable power. The Nazis were acutely aware that whoever controlled atomic secrets might control the outcome of the war itself. For 3 years, from 1940 to 1943, Bohr walked a precarious tightrope. Publicly, he continued his research, maintaining the facade of normal academic life under occupation. His institute remained open, hosting seminars and lectures as if the world hadn't turned upside down. But beneath this veneer of normalcy, Bohr was engaged in activities that would have meant certain death if discovered. The physicist had become part of an underground network, helping Jewish scientists and intellectuals escape Nazi persecution. His institute served as a way station on a secret route that spirited endangered colleagues out of occupied Europe and into the safety of Sweden or Britain. Bohr used his international reputation and diplomatic connections to arrange safe passage for dozens of scientists, often funding their escapes from his own resources. Perhaps his most audacious act of defiance involved his Nobel Prize medal. When Nazi forces occupied Denmark, Bohr faced the prospect of his gold medal being confiscated as a symbol of international recognition that the regime would either destroy or claim for propaganda purposes. Rather than surrender this symbol of scientific achievement, Bohr made an extraordinary decision. In his laboratory, surrounded by the apparatus that had revealed atomic secrets, Bohr dissolved his Nobel Prize in acid. The precious metal disappeared into solution, becoming invisible to Nazi eyes while retaining its essential nature unchanged. It was a perfect metaphor for his situation, preserving something precious by transforming it beyond recognition, hiding truth in plain sight. The acid solution sat unremarked in Bohr's laboratory throughout the occupation, just another container of chemicals among the hundreds that filled his workspace. After the war, Hungarian chemist George de Hevesy, who had helped with the dissolution, recovered the gold from the acid and had the Nobel Committee recast the medal. The Atomic Pioneers Nobel Prize literally rose from the ashes of wartime persecution. But by September 1943, the precarious balance that had allowed Bohr to continue his double life was collapsing. Nazi authorities were tightening their grip on Denmark's Jewish population, and word reached Bohr through the resistance network that the Gestapo had placed him on a list for immediate arrest. The net was closing around one of science's most valuable minds. The warning came on September 28th. Bohr had perhaps 24 hours before SS officers arrived at his door. What followed was an escape that would have challenged the imagination of any novelist, a real-life thriller played out against the backdrop of occupied Europe. As darkness fell on September 29th, Bohr and his wife, Margrethe, made their way through the blacked-out streets of Copenhagen to a predetermined rendezvous point on the coast. Every shadow might conceal a German patrol. Every footstep might herald discovery and capture. They carried nothing that would indicate their true purpose, just a middle-aged couple taking an evening stroll if anyone bothered to notice. At the coast, a fishing boat waited in the darkness, its crew part of the resistance network that had been ferrying refugees across the 20 miles of treacherous water to neutral Sweden. The boat was cramped and basic, designed for catching fish rather than carrying passengers on one of the most dangerous voyages in wartime Europe. The crossing to Sweden meant navigating waters that German patrol boats monitored constantly. Nazi mines drifted beneath the surface like deadly flowers, capable of destroying any vessel unlucky enough to trigger their mechanisms. Searchlights swept the water from shore installations, their beams creating pools of brilliant light that spelled certain capture for anyone caught within them. Hidden beneath fishing nets that reeked of salt and fish, Bohr and Margrethe endured hours of terror as their boat crept through the darkness. Every sound might herald discovery, the distant rumble of patrol boat engines, the splash of waves against hidden mines, the mechanical sweep of searchlights probing the night. The physicist who had unlocked the secrets of atomic structure found himself reduced to the most primitive human state, a fugitive hiding in darkness, depending on courage and luck for survival. The boat reached Swedish waters as dawn broke on September 30th, but Bohr's escape was far from over. British intelligence had been monitoring the situation, knowing that Bohr's knowledge of atomic physics made him one of the most valuable scientists in the world. They wanted him in London immediately, both to prevent his secrets from falling into Nazi hands and to enlist his expertise in the Allied war effort. On October 6th, Bohr climbed into what was surely one of the most unusual passenger compartments in aviation history, the bomb bay of an unarmed British Mosquito aircraft. The Mosquito was built for speed and altitude, capable of outrunning German fighters through sheer performance rather than armament. But it was never designed to carry passengers, especially not in the unpressurized bomb bay where Bohr would have to endure the journey. The flight plan called for a high-altitude dash across Nazi-occupied Norway, flying above the range of most German fighters while hoping to avoid the advanced interceptors that might catch them at maximum altitude. Bohr was given an oxygen mask and told to use it continuously, as the aircraft would be flying at altitudes where the thin air could cause unconsciousness within minutes. But something went wrong during the flight. Either the oxygen system malfunctioned, or Bohr, unfamiliar with aviation equipment, failed to use the mask properly. As the Mosquito climbed to its cruising altitude of 25,000 feet, the physicist began losing consciousness from oxygen deprivation. For crucial minutes, as the aircraft crossed the most dangerous part of its route over German-controlled territory, one of the 20th century's greatest scientific minds hung suspended between life and death in the bomb bay of a racing aircraft. The pilot, unaware of his passenger's condition, maintained course and altitude according to plan. Only when they reached the safety of British airspace and descended to lower altitudes did Bohr regain full consciousness. He had survived not only the Nazi occupation and the dangerous sea crossing, but also a brush with death at 25,000 feet above enemy territory. When the Mosquito finally touched down on British soil, Bohr emerged from the bomb bay pale and shaken but alive. British officials who met him at the airfield were startled to realize how close they had come to losing one of their most valuable wartime assets to oxygen starvation. The physicist who had revealed the quantum nature of atomic structure had nearly perished from the simple lack of oxygen in his bloodstream. But Bohr was safe, and with him came the atomic knowledge that would soon prove crucial to the Allied war effort. His escape from Nazi-occupied Denmark marked the end of one chapter in his remarkable life and the beginning of another. The man who had unlocked the secrets of atomic structure was about to help unleash the most powerful force in the universe. The journey from Copenhagen to London had taken just 1 week, but it represented a transformation from peaceful scientist to warrior in humanity's greatest conflict. The quantum realm that Bohr had explored in the calm environment of his institute was about to manifest itself in the most dramatic way imaginable, reshaping not just scientific understanding, but the very course of human history itself. Safe in London, then later in the secret laboratories of Los Alamos, Niels Bohr found himself in a position to share atomic secrets that would reshape not just scientific understanding, but the entire trajectory of human civilization. The knowledge he carried from his Copenhagen Institute was more than theoretical physics. It was the key to unlocking forces that had powered the stars since the universe began. The atomic model that Bohr had developed revealed a universe of extraordinary precision and beauty, operating at scales almost too small to imagine. But now, in the crucible of wartime urgency, these elegant quantum principles were about to manifest themselves in ways that would demonstrate both the creative and destructive potential hidden within every atom. Bohr's revolutionary insight had shown that electrons didn't orbit the atomic nucleus in random or arbitrary paths. Instead, they occupied specific energy levels, ISS, quantum states as precisely defined as the rungs of an invisible ladder. The first shell, closest to the nucleus, could accommodate only 2 electrons. The second shell could hold 8. The third shell, 18. These numbers weren't arbitrary. They emerged from the deep mathematical structure of quantum mechanics itself, as if the universe had been constructed according to a hidden numerical code. Consider the profound implications of this discovery. Every atom in your body, every atom in the air you breathe, every atom in the distant stars follows these same quantum rules. The calcium in your bones, the iron in your blood, the oxygen you depend upon for life, EGI, all of them organize their electrons according to the same fundamental principles that Bohr had uncovered in his studies of simple hydrogen. When electrons absorbed energy, ACO, from heat, from light, from chemical reactions, they could jump instantly from lower energy shells to higher ones. But these quantum leaps weren't gradual transitions. They happened instantaneously, with electrons simply vanishing from one energy level and appearing in another without traversing the space between them. It was as if nature operated according to a cosmic elevator system, where passengers could travel between floors but were absolutely forbidden from existing in the elevator shaft itself. When electrons fell back to lower energy levels, they released the absorbed energy as photons of light. The frequency of that light depended precisely on the energy difference between the initial and final electron shells. This explained the spectral signatures that had puzzled scientists for decades. Why sodium burns with that distinctive yellow glow, why copper flames dance in brilliant green, why neon signs can paint the night in colors that don't exist in the natural world. But Bohr's model revealed something even more fundamental about the nature of reality itself. At the quantum scale, particles didn't behave like tiny versions of familiar objects. An electron wasn't really a stalk, miniature sphere orbiting the nucleus like a planet around the sun. Instead, it existed as what quantum physicists came to call a probability cloud, a region of space where the electron might be found if someone attempted to observe it. This was Bohr's principle of complementarity, one of the most profound insights in the history of science. Atomic particles could be described as waves spreading through space, or as discrete particles with definite positions, but never as both simultaneously. The complete description of reality required embracing contradictory pictures, holding paradox at the heart of understanding. Imagine trying to describe the location of an electron orbiting a hydrogen atom. According to quantum mechanics, you cannot specify both its exact position and its exact velocity at the same time. The more precisely you know where it is, the less precisely you can know where it's going. The more accurately you measure its momentum, the more uncertain its location becomes. This wasn't a limitation of measurement techniques. It was a fundamental property of reality itself. Bohr realized that this uncertainty wasn't a flaw in our understanding, but a window into the deepest nature of existence. The universe, at its foundation, was probabilistic rather than deterministic. Events at the quantum scale didn't unfold according to predictable cause and effect relationships, but according to probability distributions that governed what might happen rather than what must happen. This insight challenged every assumption about the nature of physical reality. For centuries, scientists had believed that if you could know the exact position and velocity of every particle in the universe, you could predict its entire future with mathematical certainty. Bohr's discoveries revealed that such complete predictability was impossible, in principle, not just in practice. The implications extended far beyond atomic physics. If reality was fundamentally uncertain at its smallest scales, what did that mean for the larger world that emerged from quantum foundations? How could the precise, predictable behavior of everyday objects arise from components that behaved according to probability rather than certainty? Bohr's answer was that quantum uncertainty averaged out over large numbers of particles, creating the illusion of classical determinism in the macroscopic world. When trillions of atoms work together, their individual quantum uncertainties cancel each other out, producing the reliable, predictable behavior we observe in everyday life. It's like flipping a coin. While each individual flip is unpredictable, flipping millions of coins produces a statistically reliable result, very close to 50% heads and 50% tails. But there was more. Bohr's investigations revealed that atomic particles could exhibit a phenomenon that Einstein famously called spooky action at a distance, quantum entanglement. When two particles interacted and then separated, they remained mysteriously connected. Measuring the properties of one particle instantly affected the properties of its distant partner, regardless of how far apart they had traveled. This violated every classical notion of locality and causality. Information seemed to travel faster than light, effects appeared to precede their causes, and particles behaved as if they were part of a single, indivisible system, even when separated by vast distances. Einstein never fully accepted these implications of quantum mechanics, spending much of his later career searching for ways to restore classical determinism to physics. But experimental evidence consistently supported Bohr's quantum worldview. atoms really did behave according to probability rather than certainty. Particles really could exist in multiple states simultaneously until observation forced them to choose specific properties. The universe really was stranger and more wonderful than even the boldest, the imagination had suggested. In the wartime laboratories where Bohr now worked, these abstract principles were taking on urgent practical significance. Nuclear reactions, the splitting or fusion of atomic nuclei, the released energies that dwarfed anything in human experience. The binding energy that held protons and neutrons together in atomic nuclei represented nature's most concentrated form of stored power. When certain heavy nuclei like uranium-235 absorbed neutrons, they became unstable and split into lighter fragments, releasing enormous amounts of energy along with additional neutrons that could trigger further nuclear reactions. Under the right conditions, this process could sustain itself in a chain reaction that released the binding energy from countless atomic nuclei in a fraction of a second. Bohr's understanding of atomic structure was crucial to making such reactions possible. His insights into quantum mechanics helped scientists predict which isotopes would undergo fission, how to control the rate of nuclear reactions, and how to design systems that could harness nuclear energy for both peaceful and military purposes. The theoretical principles that Bohr had developed to explain the spectral lines of hydrogen were now being applied to create weapons that could destroy entire cities and power plants that could light up entire nations. The journey from pure scientific curiosity to world-changing technology had taken less than 3 decades. As Bohr worked alongside other brilliant scientists in the secret laboratories of the Manhattan Project, he understood that they were not just splitting atoms, they were splitting history itself. The quantum realm that he had first glimpsed in his Copenhagen laboratory was about to emerge into the macroscopic world with a power that would forever change the relationship between humanity and the forces of nature. The atom had revealed its architecture, and that architecture contained energies that made the power of chemical explosives seem like fireflies compared to lightning bolts. The quantum genie was about to escape its atomic bottle, carrying with it both the promise of unlimited clean energy and the threat of unprecedented destruction. The beautiful mathematical principles that governed electron shells and spectral lines were about to reshape human civilization itself. The theoretical insights that Niels Bohr had developed in the quiet halls of Copenhagen were about to transform human civilization in ways that even he could not have imagined. Like seeds carried on the wind to fertile ground, his discoveries about atomic structure would take root in laboratories around the world, growing into technologies that would touch every aspect of human life. The first transformation came through our understanding of how electrons behave in solid materials. Bohr's revelation that electrons occupy specific energy levels in atoms led scientists to discover that in crystalline solids, these individual atomic energy levels merge into bands, regions where electrons can exist, separated by gaps where they cannot. This band structure determines whether a material conducts electricity like a metal, blocks it like an insulator, or does something far more interesting, acts as a semiconductor. In 1947, 3 scientists at Bell Laboratories, AOC, John Bardeen, Walter Brattain, and William Shockley, used this understanding of electron behavior to create the first transistor. This device, no larger than a pencil eraser, could amplify electrical signals and switch currents on and off by controlling how electrons moved through carefully prepared semiconductor materials. The transistor represented the practical application of quantum principles that Bohr had discovered. By adding precise amounts of impurities to pure silicon or germanium crystals, engineers could create materials where electron behavior could be controlled with extraordinary precision. A small voltage applied to one part of the device could dramatically alter the electrical properties of the entire structure, creating an electronic switch faster and more reliable than any mechanical system. Consider the magnitude of this transformation. The The room-sized computers of the 1940s, filled with thousands of glowing vacuum tubes that generated enormous heat and failed frequently, could be replaced by solid-state devices with no moving parts, no filaments to burn out, and power consumption measured in millionths of watts rather than thousands. But the transistor was just the beginning. As manufacturing techniques improved, engineers learned to create ever smaller transistors, eventually packing millions, then billions of them onto silicon chips smaller than your fingernail. Each of these microscopic switches operates according to the quantum mechanical principles that Bohr first described: electrons jumping between energy levels, following probability distributions, behaving sometimes like particles and sometimes like waves. The smartphone in your pocket contains more than 10 billion transistors, each one a quantum mechanical device that traces its conceptual lineage directly back to Bohr's insights about atomic structure. Every calculation your computer performs, every image on your screen, every message you send across the internet depends on the controlled manipulation of electrons, according to quantum principles discovered in the study of hydrogen spectra. Meanwhile, other applications of Bohr's discoveries were illuminating the world in entirely new ways. His insight that electrons could be forced to emit light in perfect synchronization led to the development of lasers, devices that produce beams of coherent light with properties unlike anything found in nature. The first laser fired on May 16, 1960, in the laboratory of Theodore Maiman at Hughes Research Laboratories. Maiman had created a synthetic ruby crystal in which chromium atoms were embedded in a precise lattice of aluminum oxide. When intense light from powerful flash lamps excited the chromium atoms, their electrons jumped to higher energy levels, then fell back down in perfect unison, releasing photons that traveled in exactly the same direction, with exactly the same frequency. The result was a beam of light so pure and concentrated that it could cut through steel, travel to the moon and back without significant spreading, or carry vast amounts of information through fiber optic cables. Laser light behaves like a perfectly organized army of photons, all marching in step and moving in the same direction, in contrast to ordinary light, which resembles a chaotic crowd of photons traveling in random directions. Today, lasers read the information stored on compact discs and DVDs, enable precise surgical procedures that can repair detached retinas without damaging surrounding tissue, and carry internet traffic through transcontinental cables at the speed of light. Industrial lasers cut and weld materials with precision measured in fractions of millimeters, while laser printers create text and images by controlling exactly where photons strike photosensitive surfaces. Each laser operation depends on the controlled manipulation of electron energy levels in atoms, the same quantum leaps that Bohr first described in his model of hydrogen. The beautiful colors of light that emerge when elements are heated in flames have been harnessed to create tools that extend human capabilities far beyond what previous generations could have imagined. Medical technology, too, has been revolutionized by understanding atomic structure. Magnetic resonance. Imaging scanners work by manipulating the magnetic properties of atomic nuclei, particularly hydrogen nuclei, in water molecules that make up much of the human body. When placed in powerful magnetic fields, these nuclei align like tiny compass needles, radio waves. You can then flip them into different orientations, and as they return to their aligned state, they emit radio signals that reveal the density and type of tissue throughout the body. This technique allows doctors to see inside living patients without surgery, radiation, or any invasive procedures. Brain tumors become visible as shadows in detailed images that show the architecture of thought itself. Torn ligaments appear as disruptions in the organized structure of healthy tissue. Heart defects reveal themselves through changes in blood flow patterns that become visible through quantum mechanical interactions between radio waves and atomic nuclei. Solar panels represent another triumph of quantum mechanical engineering. When photons of sunlight strike specially prepared silicon surfaces, they can transfer their energy to electrons, knocking them loose from their atomic bonds and creating electrical current. This photovoltaic effect, first explained by Einstein using quantum theory, enables the direct conversion of light into electricity. Modern solar installations can convert more than 20% of incoming sunlight into electrical energy, providing clean power for everything from pocket calculators to entire cities. Each photon that strikes a solar panel participates in a quantum mechanical transaction that liberates an electron, demonstrating how the theoretical insights of early 20th century physics have become practical solutions to 21st century energy challenges. Nuclear power represents perhaps the most dramatic application of atomic knowledge. Nuclear reactors operate by carefully controlling the fission of uranium nuclei, splitting atoms to release the binding energy that holds their cores together. A single uranium nucleus, when split by neutron bombardment, releases more than 40 million times as much energy as burning a single carbon atom in coal. This enormous energy density means that nuclear fuel the size of a softball can power a city for months, while the equivalent energy from coal would require millions of tons of material. Nuclear submarines can operate underwater for months without refueling, and nuclear power plants can generate electricity continuously for years between fuel changes. The controlled nuclear reactions that power these systems depend on understanding the quantum mechanical properties of atomic nuclei, how they absorb neutrons, how they become unstable, how they split into lighter fragments while releasing additional neutrons to sustain chain reactions. Every aspect of nuclear reactor design relies on principles that trace back to the atomic models that Bohr and his contemporaries developed. Even the most mundane aspects of modern life depend on quantum mechanical technologies. The LED lights that increasingly illuminate our homes and cities work by forcing electrons to jump between energy levels in semiconductor materials, converting electrical energy directly into light with extraordinary efficiency. Fluorescent lighting operates through quantum mechanical interactions between mercury atoms and phosphor coatings that convert ultraviolet radiation into visible light. The liquid crystal displays that show information on everything from digital watches to massive television screens work by controlling how light polarization changes as it passes through materials whose molecular orientation can be adjusted by electrical fields. Each pixel on your computer screen represents a microscopic application of quantum mechanical principles to control the behavior of light and matter. These technologies represent more than just practical applications of scientific knowledge. They demonstrate how understanding the fundamental structure of reality enables us to manipulate that reality in ways that were once indistinguishable from magic. The journey from Bohr's theoretical insights about hydrogen spectra to the smartphone in your pocket represents one of the most remarkable transformations in human history. Yet we are still in the early stages of learning to harness quantum mechanical principles. The technologies that currently surround us use quantum effects in relatively simple ways, controlling electron behavior in semiconductors, manipulating atomic energy levels in lasers, exploiting nuclear binding energies in reactors. The next generation of quantum technologies promises to be far more sophisticated, using the full weirdness of quantum mechanics, superposition, entanglement, and uncertainty to perform tasks that no classical system could accomplish. The quantum realm that Bohr first revealed is about to emerge into our everyday world in ways that will make today's technologies seem as primitive as steam engines compared to space shuttles. As we stand at the threshold of the 21st century's third decade, we find ourselves witnesses to a second quantum revolution, one that would astonish even Niels Bohr himself. The principles of quantum mechanics that he helped discover are no longer confined to the invisible realm of atoms. They are emerging into our macroscopic world, promising to transform human civilization as profoundly as the first wave of quantum technologies transformed the 20th century. In laboratories around the world, scientists have learned to manipulate individual atoms with a precision that borders on the magical. Scanning tunneling microscopes can pluck single atoms from surfaces and arrange them into patterns that spell words or create materials with properties that don't exist anywhere in nature. Researchers at IBM have spelled out company logos using individual xenon atoms positioned on copper surfaces, demonstrating humanity's growing mastery over matter at its most fundamental level. This atomic-scale engineering represents more than just a technological tour de force. Yes, ni. It reveals our deepening relationship with the quantum realm that Bohr first helped us understand. We are learning to be architects of reality itself, designing materials by arranging their atomic components according to precise specifications. Consider the implications. Traditional materials science has always been limited by what nature provides, the properties of elements as they exist in the periodic table, the characteristics of compounds as they form through chemical bonding. But when we can position individual atoms wherever we choose, we enter a realm of unlimited possibility. We can create substances with any combination of properties we desire, materials that are simultaneously lightweight and incredibly strong, conductors that carry electricity without resistance, surfaces that repel water while attracting specific molecules. Perhaps the most extraordinary development emerging from our quantum understanding is the quantum computer. Unlike the digital computers that surround us today, which process information using bits that must be either 0 or 1, quantum, computers use quantum bits, AAS, qubits, that can exist in multiple states simultaneously through the principle of superposition that Bohr helped discover. Imagine a classical computer trying to find its way through a vast maze. It would have to try each possible path sequentially, potentially requiring millions of years to find the exit through trial and error. A quantum computer, however, could explore all possible paths simultaneously, like a ghostly presence that walks through walls and travels multiple routes at once, finding the solution in minutes or hours rather than millennia. Major technology companies and research institutions have built quantum processors containing hundreds of carefully controlled qubits, each one a quantum mechanical system that stores and processes information according to the probabilistic rules that govern atomic behavior. These devices operate at temperatures colder than outer space, where thermal vibrations won't destroy the delicate quantum states that enable their extraordinary computational abilities. Google achieved what they called quantum supremacy in 2019, demonstrating that their quantum processor could perform a specific calculation in 200 seconds that would take the world's most powerful classical supercomputer 10,000 years to complete. IBM, Intel, and dozens of other companies are racing to build ever more powerful quantum systems that could revolutionize everything from drug discovery to financial modeling to artificial intelligence. But quantum computing represents just one facet of the quantum technologies now emerging from research laboratories. Quantum sensors exploit the exquisite sensitivity of atomic systems to measure physical phenomena with unprecedented precision. The Laser Interferometer Gravitational Wave Observatory uses quantum mechanical effects to detect gravitational waves from colliding black holes billions of light-years away, measuring distortions in space-time smaller than 1/10,000th the width of a proton. These quantum sensors could revolutionize navigation, medical imaging, and fundamental physics research. Quantum magnetometers can detect magnetic fields millions of times weaker than Earth's magnetic field, potentially enabling early detection of Alzheimer's disease by measuring the magnetic signatures of neural activity. Quantum accelerometers could provide navigation systems that work deep underground or in space, where GPS signals cannot reach. The future promises even more extraordinary applications. Scientists envision quantum networks that use entangled particles to transmit information with perfect security, protected by the fundamental laws of physics rather than mathematical encryption that could potentially be broken. These quantum internet connections would enable secure communication that becomes more secure when someone tries to eavesdrop, using the quantum mechanical principle that observation changes the system being observed. Fusion power, the energy source that drives the stars themselves, may finally become practical through our improved understanding of plasma physics and quantum mechanical processes. Fusion reactors would fuse hydrogen nuclei to create helium, releasing enormous amounts of energy while producing no radioactive waste and using fuel that could be extracted from ordinary seawater. Several experimental fusion reactors are approaching the break-even point, where they produce more energy than they consume, potentially solving humanity's energy needs for millennia to come. The International Thermonuclear Experimental Reactor, currently under construction in France, will test whether controlled fusion can provide clean, abundant energy by recreating the nuclear processes that power the sun. Success would mean access to virtually unlimited clean energy, transforming everything from transportation to manufacturing while eliminating the carbon emissions that drive climate change. Quantum biology is revealing that quantum mechanical effects play crucial roles in biological processes that sustain life itself. Photosynthesis, the process that converts sunlight into chemical energy in plants, appears to use quantum coherence effects to transfer energy with nearly perfect efficiency. Birds may navigate using quantum entanglement in specialized proteins that sense Earth's magnetic field. Even consciousness itself might depend on quantum mechanical processes in neural microtubules, though this remains highly speculative. These discoveries suggest that life has been exploiting quantum mechanical principles for billions of years, evolving biological quantum technologies that we are only beginning to understand. As we learn to mimic these natural quantum processes, we may develop new forms of solar energy conversion, magnetic field sensing, and perhaps even quantum-enhanced computation inspired by biological systems. The boundaries between the quantum and classical worlds are dissolving before our eyes. Researchers have demonstrated quantum effects in objects large enough to see with the naked eye, opening possibilities for macroscopic quantum devices that could bridge the gap between the microscopic quantum realm and our everyday classical experience. Perhaps most remarkably, our growing mastery of quantum mechanics is leading to new insights about the nature of reality itself. Quantum computers could simulate complex quantum systems that are too complicated for classical computers to model, potentially revealing new physical principles or solving mysteries about how the universe works at its deepest levels. Some scientists speculate that sufficiently powerful quantum computers might simulate entire universes, exploring how different physical laws would affect the evolution of matter and energy over cosmic timescales. Others suggest that quantum technologies could enable new forms of space exploration, using quantum sensors to detect dark matter or quantum communication systems to maintain contact with spacecraft across interstellar distances. As we stand on the threshold of this quantum future, we can sense that we are living through a transformation as significant as the agricultural or industrial revolutions. The principles that Niels Bohr first glimpsed in his study of hydrogen atoms are becoming the foundation for technologies that will reshape every aspect of human civilization. The boy who once played football in Copenhagen and wondered about the nature of atoms could never have imagined that his insights would lead to computers that think in quantum superposition, materials assembled atom by atom according to human design, and energy systems that harness the same nuclear forces that light the stars. Yet perhaps Bohr would not be entirely surprised. He understood that the quantum realm operates according to principles that challenge human intuition, where impossible things become routine, and where the act of observation changes reality. He knew that once humanity learned to think quantum mechanically, we would discover capabilities that seemed indistinguishable from magic. The quantum future is not a distant dream, but an emerging reality. In laboratories around the world, in technology companies racing to commercialize quantum devices, in the minds of young scientists who have grown up in a quantum world, the next chapter of human technological evolution is already being written. The atom has revealed not just its secrets, but its potential. The invisible architecture that Bohr helped us understand is becoming the visible foundation of tomorrow's world. We are learning to speak the language that nature uses to construct reality itself, and in that language, we are writing the next chapter of human civilization. The greatest adventure in the history of science continues, carrying us toward horizons that even Bohr, in all his visionary brilliance, could never have imagined. The quantum realm that he helped reveal has become our new frontier, and we are its explorers, pioneers venturing into territories where the impossible becomes inevitable and where the very foundations of reality await our discovery and mastery. The story that began with a simple question about the nature of matter has become the story of humanity's growing power to shape the universe itself, one atom at a time.